Okay, so I'm going to go through the first few questions of the Practice AS paper, Pure and Mech paper that I set you. We'll see how it goes. There might be questions that are a bit tricky. But anyway, I'll go through them and I'll try and explain my thinking, what you should be thinking as we go along. So the first question is a trigonometric equation question. Solve the equation cos 2 theta equals 0.3 for 0 to 360 degrees. I'm going to quickly write the question out. Cos 2 theta equals 0.3, and we've got to get all the answers in the range 0 to 360. Now you've got a cos 2 theta here, okay? What I've taught you to do, I think I have anyway, is to make a substitution. So make an alpha substitution. Alpha is 2 theta. Right? And we have to write a new range for alpha. Okay, well alpha is double theta, so double 360 is 720, double 0 is 0. So this is the new range, okay, and the question has become cos alpha equals 0.3. So we're going to solve this equation in this range and get all the alpha values. Okay, so I'm going to start making my list. Here's my calculator. Let's try and get it out of the glare of the light. So I'm going to make sure I'm in degree mode, which I am, and I'm going to do inverse cos of 0.3. That gives me my first alpha value of 72.54. Okay, I'm going to write it down to 1 decimal place. Now then, there's more than one answer, of course, and we need to think about what the cos graph looks like in order to get these answers. The cos graph starts at 1, and cycles like this, and up to there, that's 300 degrees because that's a full cycle, and then it starts again. So this is plus 1 on the y-axis, this is minus 1. So we're looking for 0.3, which is about here, and there is the 72, right where the pen is there. There's the 72. So the next one that also is 0.3 here, what you might notice if I just draw a line down there is there's perfect symmetry here down the middle. So if we've got 72 up from this end, we'll also have 72 back from 360. So I'm going to do 360 minus 72.5 on my calculator. I'm using the answer to maintain accuracy. We get 287.5. Okay, that's the first two answers, but there's going to be more in this range. And the nice thing about a cos graph is you should be able to see that just the same numbers shifted along. So what I'm trying to say is the gap between there and this equivalent thing here, same part of the curve, look, coming down at maximum. So these two bits are 360 apart. So the next answer is 360 plus 72.5. Now I should have stored 72.5 in the memory, shouldn't I? So I'm going to call it back up. There it is. Probably always a good idea to store it. I've stored it in A. Now I'm going to do 360 plus A, 432.5. Okay, and then I need this number plus 360 degrees. Well, to be fair, it's not going to round any differently, so I could just type this one in this time, right? And there we go. Okay, so those are the alpha values. And now I'm going to half these, because these are alpha values and we want theta values. If alpha equals 2 theta, theta will be alpha divided by 2. About rearranging this to get theta on its own, you'd want to take that 2 and stick it under there. You get this. So I have to divide all these by 2. Okay? I have just realised I've made a bit of a mess of the accuracy a little bit because I've rounded at this stage. And really, you don't want to round until the very end, do you? So yeah, I have made a bit of a mess of this. What I'm going to do is get all these stored in A, B, C, D exactly. So there's A. This one is 360 minus that. Set that up here in the graph. So I'm going to store that in B. Okay. This one is this plus 360. So that's A plus 360. There it is. I'm going to store that in C. And this one is B plus 360. Alpha B plus 360. And I'm going to store that in D. So I've got them all really fully accurate in A, B, C and D. I'm now going to halve them and then round these up. I may have got away with it, to be honest, but I'm just being extra safe with the rounding. So that number to 1 decimal place is there. B divided by 2 and then rounded to 1 decimal place there. Next one, C divided by 2 then rounded to 1 decimal place there. And the last one, alpha D divided by 2 1 decimal place, that one there. So there are the answers, and of course you can check them, and I'm quickly going to check one. I'm going to check this one by replacing it in the original. So I'm going to replace it in the left hand side. I'm going to do cos of 2 lots of D, well not D, this number, cos of 2 lots of this number, see if I get 0.3. Here we go. I'm going to press equals, cos 2 lots of answer is 0.3. So at least I've checked that one. That's that question done. The crucial bit they're testing is the substitution, changing of the range. Okay, that took a bit longer than I imagined, but never mind. Question number 2. James tries to solve the inequality x squared minus 4x minus 14 is greater than or equal to 0. He writes his answer as that. So you've got set notation there. The left hand side between those squiggly brackets is saying all x values less than or equal to 2. The right hand side is saying all x values that are less than 7. And the bit in the middle is a U. That's a union. So that means both of those things. So I'm just going to get rid of some of it because I'm not sure we need all of that notation. So we've got this and we've got this. Okay. Correct all errors in his answer. Well, I suspect there's going to be a problem that these two inequalities face the same way. So I'm going to just solve the inequality myself first. May not need to solve the inequality, but this is going to help you revise quadratic inequalities. So we're going to factorize this. Okay, two numbers that multiply to make minus 14 and add to make minus 5 is going to be minus 7 and 2. Okay, and now what I'm going to do is draw the graph. Sketch the graph. So this graph will go through the x-axis at minus 2 and plus 7. And it's a positive x squared. It's a U shape. Alright? In fact, that there will be negative 14. Doesn't really look to scale, but doesn't really matter. And the original inequality is saying, where is this bigger than or equal to 0? Well, we've set all of this here, same as this, to be equal to y. So this is the same as y. Okay? This is the same as y. So I'm interested in when y is bigger than or equal to 0 on this graph. When is y bigger than or equal to 0? It is for that number there, 7. When you put 7 in, you get 0, and it says all equal to 0. This number here, and up here, look, these are all y values bigger than or equal to 0. So we're talking the x values from that black dot upwards and the x values from that black dot backwards. So the solution, in the form that I would want to write it, would look like this. Okay? So let's correct his answers. He's got the first squiggly line, squiggly bit correct, I'd say. Oh, except he said 2. Whoops. So I've made one correction there. I'm going to have a think about that U symbol. I'm going to leave that for a minute. Okay, and so I've turned that inequality around, and I've added an or equal to. Now then, let's go back to this. So it's basically either going to be U, which means union, so that means like one thing or the other, or both, or it's and, intersection. Okay, well, these two sets can't intersect, can they? Here you're talking about a load of x values less than -2. Here you're talking about a load of x values above 7. There is no intersection. They don't overlap. So that one just doesn't make any sense to write at all. It has to be the U. So I think he's got the U correct, and I think that's the answer. Okay? Right, I'm going to move over to question 3 now. You can pause this if you want to have a longer look at it. Okay, I'm going to be a bit sneaky, I think, and just turn my page around. Okay, I'll try and cover this up a bit so you don't get distracted. Right, let's move it over. Oh, there's a 2 floating around in space. Get over that. So, question 3. A block of mass 5 kilograms is in equilibrium on a rough horizontal table. It is connected by horizontal light inextensible strings over smooth pulleys to particles of mass m kilograms and 2m kilograms which hang freely as shown in figure 3. Find the frictional force acting on the block, clearly stating its direction. So I'm going to do a quick diagram. Just realised you're enjoying the washing machine humming away in the background. The joy that is. Okay, let's put some forces on. This is 5m g newtons. Okay, that will also be 5 mg newtons. And we've got 2 pieces of string. Okay, it says it is connected by horizontal light inextensible strings. So this is one string, this is another. Okay, we're going to have a tension in this string and a weight there, 2 mg. I'm going to label this tension T. That's also going to pull down on the pulley, and it's going to pull that mass this way, isn't it? The effect of this mass on this one is to try and pull it this way. Well, I've got that arrow there. Then you're supposed to put another one there. These 2 arrows aren't all that important. They show what's happening on the pulley, but you never really get asked questions about forces on pulleys. But I'm going to put it in for completeness anyway. I've labelled those T's as T1s because there'll be a different T over here. Okay, I'm going to have similar looking arrows pointing in similar sorts of directions. Okay, and then this is mg. Okay, and if the mass is going to go that way, because this is the bigger mass than that one, this mass here is going to hold it back, isn't it? It's going to stop it going that way, and it has its effect on the mass through that arrow there. Okay, so that's how you label your diagram up. I've labelled all the forces. I might as well write 5 mg newtons here. These are all in newtons, these forces. But there it is. It's looking a little bit busy, but there we are. There is a frictional force acting on the block, which I've got to find. Okay, it's hanging in equilibrium, so in fact, it's not going anywhere. Well, if it's not going anywhere, you need to look at these 2 masses. This is the heavier mass. So it wants to go clockwise. Whole system. That wants to go up. That wants to go right. This wants to go down. Wants to go that way. If it's being held in equilibrium, there must be another force holding it back. Okay, and that's the frictional force there. Probably shouldn't have drawn it up there actually. People would tend to draw it there along the table because that's kind of where it acts. It's acting between the base of the mass and the surface of the table. So there it is. I'm going to get some marks, some of the 3 marks for writing that F there. What I've got to do now is figure out what the F is. Okay. What we've got to remember is the whole thing is in equilibrium. So if you look at any mass on that diagram and look at all the forces on the mass, they will all cancel each other out. So I'm going to say, let's look at the 2m mass. If you look at the 2m mass, there's T1 going upwards and 2mg going downwards. They've got to be the same. They've got to be equal and opposite if it's equilibrium. So there, I straight away know that T1 is 2mg. If I look at the m mass, I'm going to draw that here. There's the m mass. Again, this is in equilibrium, so T2 must be mg. 1 mg, if you like. I'm going to put the 1 in. So I've now got the tensions in terms of the m's. And now I'm going to look at the 5m mass. Okay, and what I'm doing now is I'm going to ignore these 2 forces because they cancel each other out. I'm going to write an equation for the horizontal forces. This is called resolving horizontally. Resolve horizontally. And if it's in equilibrium, so if in equilibrium, rightwards forces equals leftwards forces. Similarly, upwards will equal downwards. Worried about that. So the rightwards forces are T1. And the leftwards forces on the 5m kilogram mass are T2 plus F. They're acting in the same direction, so we add them together. And now I'm going to substitute these values for T1 and T2. T1 is 2 mg. T2 is 1 mg. Okay, and now hopefully you can see I'm going to subtract 1 mg from both sides, and I will get that. mg newtons. Okay, you might sort of slightly worry that you haven't found it as an individual number, but everything in this question is done in terms of m. So that is the. Okay, I'm going to stop this video here and carry on with the rest of the questions separately.